A vast and infinite universe has always held secrets beyond our wildest imaginations, and often these enigmas prevent the sharing of information crucial to the advancement of science. Recently, the most advanced telescopes have detected a phenomenon that defies all logic, a cosmic mystery that has left scientists around the world perplexed. Findings from the James Webb Space Telescope have called the Big Bang Theory into question. Joel Rogan takes a deeper look at this telescope's latest discovery, which has revealed the shocking disappearance of 900 trillion stars. The 10 billion James Webb Space Telescope has been operational in space for over 2 years, but the results already prove that this investment has been worth it. The telescope far surpasses Hubble, providing unprecedented views of deep space. In July 2022, the James Webb began exploring extremely long wavelengths coming from distant galaxies, detecting radiation outside the visible range known as redshifted ultraviolet. The telescope has revealed astonishing details that were beyond our expectations, showing areas of space that Hubble could not observe. Most disturbingly, however, James Webb has discovered the unexplained disappearance of 900 trillion stars in the vacuum of space. This finding raises disturbing questions about how these stars could have disappeared without a trace, and each new piece of data adds an air of mystery and concern. In a surprising observation, the James Webb Telescope has detected the disappearance of trillions of stars without a trace. The question is, where have they gone? There are 2 main theories about this phenomenon. The first suggests that the stars are still present, but their death could have been accompanied by a lower luminosity, perhaps hidden by dust, or that they have simply collapsed into black holes without going through a supernova stage. The second theory is more alarming. It could be that the universe is in a process of disappearance that we cannot stop. Almost a century has passed since scientists theorized that the universe was expanding and that the most distant galaxies appear to be moving away from us at an ever-increasing speed. This expansion does not mean that galaxies are physically moving through space, but that the fabric of space itself is expanding, leading galaxies to move away more quickly. This model, which has been dominant since the 1920s, has recently been revised. Only 20 years ago, it was discovered that this expansion is accelerating. As time goes on, galaxies are moving away from us at an ever-increasing speed, becoming unreachable even if we were traveling at the speed of light. When we look at the stars whose light has traveled for 100 years to reach us, we are seeing that star 100 light-years away. However, when we look at a galaxy whose light has traveled for 100 million years, we're not looking at a galaxy that is 100 million light-years away. In fact, that galaxy is even farther away. The reason for this is that, on larger scales such as galaxies and clusters, the expansion of the universe plays a major role. The longer it takes for light to reach us, the farther away the galaxy is due to the expansion of space. This phenomenon manifests itself as a redshift. As light passes through expanding space, it stretches and changes its wavelength. If the universe were not expanding, the wavelength of the light reaching us would be constant. But due to its expansion, the wavelength stretches, causing the light to be redshifted. The significant redshifts we have observed in the most distant galaxies strongly confirm that the universe is expanding. However, our task goes beyond simply verifying this expansion. We can use the information gathered to understand how the universe has changed over time and what it is made out of. When light from a distant cosmic source struggles through the expanding universe, its wavelength is stretched, producing a redshift. This effect is more pronounced for objects that are farther away since their light has been traveling for much longer. By measuring the redshift of various sources at different distances and comparing their size and intrinsic brightness to what we can observe, we can reconstruct the full history of the universe's expansion. In addition, the way the universe expands is determined by the different types of matter and energy present in it. This allows us to learn about its composition. Approximately 68% of the universe is made of dark energy, equivalent to a cosmological constant. 27% is dark matter, and about 4.9% is made up of protons, neutrons, and electrons. Only 0.1% is made of neutrinos and antineutrinos, and 0.08% is photons. No other entities, such as cosmic strings or textures, are found. Knowing these components with such precision allows us to apply the laws of gravity, according to Einstein's theory of general relativity, to predict the future fate of the universe. In doing so, we discover that the universe is dominated by dark energy. This finding implies that galaxies that are not gravitationally bound to us will eventually move away at ever-increasing rates. As the universe continues to expand unchecked, the distance between us and those galaxies will increase, making them appear to be moving away at an increasing speed. This leads to an even more disturbing conclusion. At a critical distance, the fabric of space itself expands the distance such that a photon living in our galaxy for a distant galaxy will never reach us. The expansion rate of the universe is so rapid that distant galaxies are becoming unreachable to us, even if we could travel at the speed of light. Although those galaxies are only 18 billion light-years away, the overall expansion is still increasing, and the density of matter and radiation continues to decrease. Our observable universe is about 46 billion light-years across, and if we consider that all regions of space contain an even number of galaxies, only 6% of all galaxies in the current universe are accessible to us. This means that even if we were to travel at the speed of light today, we would only be limited to exploring a small fraction of the universe. Furthermore, between 20,000 and 60,000 stars go from reachable to unreachable every second. Although the light emitted by these stars a second ago will eventually reach us, the light they emit in the present never will. This fact is unsettling, but it also reminds us of how precious every moment is. From a more optimistic perspective, this reality reminds us that if we ever want to travel beyond our local group of galaxies, which includes Andromeda, the Milky Way, and about 60 satellite galaxies, every second that passes is a lost opportunity. Of the estimated 2 trillion galaxies in the current universe, only 6% are still accessible from the Milky Way, and this percentage is still decreasing. This means that 94% of the galaxies in our observable universe are already out of reach due to the accelerated expansion caused by dark energy. As time goes on, every galaxy outside our local group is destined to move even further away unless we develop the ability to travel to other groups and clusters of galaxies. Otherwise, humanity will remain trapped in our local group, and our ability to send or receive signals from the various parts of the vast cosmos will fade away. The accelerated expansion of the universe is relentless, and the gravity we possess is not enough to counteract it. The universe is constantly expanding, and unfortunately, there's nothing we can do about it. The understanding of the cosmos has evolved tremendously over the past century, fueled by breakthroughs in both technology and theoretical physics. One of the most significant advancements has been the development of space telescopes, such as the Hubble and James Webb Space Telescopes. These observatories have opened up new frontiers in our understanding of the universe, allowing us to explore regions that were previously beyond our reach. Each new discovery raises more questions than answers, leading to an ever-deepening sense of awe and curiosity about the vast expanse of space. One of the key challenges in modern astronomy is the study of exoplanets, planets that orbit stars outside of our solar system. Since the first exoplanet was discovered in 1992, thousands have been identified, and many of them are in what scientists call the habitable zone. This is the region around a star where conditions may be right for liquid water to exist on the planet's surface, a key ingredient for life as we know it. The search for Earth-like exoplanets has become one of the most exciting areas of scientific inquiry, as it could lead to the discovery of extraterrestrial life. One of the primary methods used to detect exoplanets is the transit method, which involves observing the dimming of a star's light as a planet passes in front of it. By measuring the amount of light blocked, astronomers can determine the planet's size, orbit, and distance from its star. The James Webb Space Telescope, with its unprecedented infrared capabilities, is expected to play a major role in this field, allowing scientists to study the atmospheres of exoplanets in greater detail than ever before. This could potentially help us detect signs of life or the conditions necessary for life on planets light-years away. Beyond exoplanet discovery, the study of cosmic inflation has become a crucial area of interest. Cosmic inflation is the theory that the universe underwent an extremely rapid expansion during the first few moments after the Big Bang. This expansion was so fast that regions of space that were once close together are now separated by vast distances, making it impossible for light to travel from one point to another. The theory of inflation helps explain the uniformity of the universe and the large-scale structures we observe today, such as galaxies and clusters of galaxies. By studying the remnants of this inflationary period, known as the cosmic microwave background radiation, CMB, scientists can gain insight into the early conditions of the universe. The CMB is often referred to as the afterglow of the Big Bang. It is the faint radiation left over from the hot, dense state of the early universe. The detection of the CMB in 1965 by Arno Penzias and Robert Wilson was a pivotal moment in cosmology, providing strong evidence for the Big Bang theory. Since then, advancements in technology have allowed scientists to map the CMB with incredible precision. The most detailed map of the CMB was produced by the European Space Agency's Planck satellite, and these measurements have provided crucial insights into the age, composition, and shape of the universe. One of the most profound implications of the CMB is the evidence it provides for the existence of dark matter and dark energy. These mysterious substances make up about 95% of the universe, yet they remain largely invisible and undetectable by traditional means. Dark matter is thought to be responsible for the gravitational effects observed in galaxies and galaxy clusters, while dark energy is believed to be driving the accelerated expansion of the universe. Despite decades of research, scientists are still unsure of the exact nature of these elusive entities. However, their existence is essential for explaining many of the phenomena observed in the cosmos. Dark matter, for example, was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who noticed that galaxy clusters were moving in a way that suggested there was more mass present than could be accounted for by the visible matter alone. Since then, numerous other observations have pointed to the existence of dark matter, including the rotation curves of galaxies, gravitational lensing, and the behavior of galaxy clusters. However, despite its gravitational effects, dark matter does not emit, absorb, or reflect light, making it incredibly difficult to detect directly. Dark energy, on the other hand, was discovered in 1998 through the observation of distant supernovae. These supernovae appeared to be farther away than expected, suggesting that the expansion of the universe was accelerating. This led scientists to propose the existence of dark energy, a mysterious force that counteracts gravity and drives the universe's expansion. Unlike dark matter, which clumps together under the influence of gravity, dark energy seems to have a repulsive effect, causing galaxies to move away from each other at an ever-increasing rate. Understanding dark energy is one of the most pressing challenges in modern cosmology, as it holds the key to understanding the ultimate fate of the universe. Another fascinating area of research is the study of black holes. These enigmatic objects, with their immense gravitational pull, have long captured the imagination of scientists and the public alike. Black holes are formed when massive stars collapse under their own gravity, creating a region of space where the gravitational field is so strong that not even light can escape. The boundary surrounding a black hole is known as the event horizon, and once something crosses it, there is no way to retrieve it. Black holes come in different sizes, ranging from stellar mass black holes, which are a few times the mass of the Sun, to supermassive black holes, which can be billions of times more massive than the Sun and are found at the centers of most galaxies, including our own Milky Way. The study of black holes has made great strides in recent years, especially with the advent of the Event Horizon Telescope, EHT. In 2019, the EHT produced the first-ever image of a black hole, located at the center of the galaxy M87. This groundbreaking achievement provided direct evidence of the existence of black holes and opened up a new era in astrophysics. The image showed the shadow of the black hole surrounded by a bright ring of light, which is created by the intense gravitational forces that bend light around the event horizon. This image not only confirmed many of the predictions of Einstein's general theory of relativity, but also raised new questions about the nature of black holes and their role in the evolution of galaxies. One of the most intriguing aspects of black holes is the possibility that they could be connected to other parts of the universe through what are known as wormholes. Wormholes are theoretical passages through spacetime that could, in principle, allow for faster-than-light travel between distant regions of the universe. While wormholes have yet to be observed, they are a natural consequence of the equations of general relativity and have been the subject of much speculation. If they exist, wormholes could offer a way to bypass the vast distances between galaxies and potentially make intergalactic travel a reality. However, there are many challenges that would need to be overcome before such travel could be achieved, including the creation and stabilization of a wormhole and the potential dangers posed by the extreme gravitational forces near a black hole. The future of space exploration is equally exciting. Advances in propulsion technology, such as the development of ion drives and nuclear fusion engines, could one day enable us to travel to distant stars and explore exoplanets up close. Missions like NASA's Artemis program, which aims to return humans to the moon by 2024, are just the beginning of humanity's journey into deep space. The ultimate goal of these missions is to establish a sustainable presence on the moon and eventually send astronauts to Mars. While the challenges of space travel are immense, the rewards are equally great. Not only could we gain valuable insights into the nature of the universe, but we could also ensure the long-term survival of humanity by establishing a foothold beyond Earth. As our understanding of the universe continues to grow, so too does our sense of wonder and curiosity. Each new discovery raises more questions, pushing the boundaries of what we know and challenging our understanding of the cosmos. The universe, with its vastness and mysteries, continues to inspire awe and excitement, and it is likely that future generations will make even greater discoveries that will shape our understanding of the universe and our place within it.